In this video, we're going to calculate the pH of a weak base solution um, given some information such as Kb and also initial concentration. So here we have a weak base called hydrazine. So calculate the pH of a 0.5 mole per liter aqueous solution of hydrazine. The Kb of hydrazine is 1.7 times 10 to the power of negative 6. We can go take a look at hydrazine over here in our table. So if it's included here. So notice it's a weak base. If you weren't sure, you could just come and take a look. It's included in the weak base table. Here's hydrazine, N2H4. And we're given the Kb value over here of 1.7 times 10 to the power of negative 6. Sometimes you might have different values depending on the table, depending on the condition. So we're going to use what's given in the question. So this is a weak base. We can't assume that 100% of it's going to dissociate. We have to write an equation for this weak base. So remember, according to our Bronsted-Lowry theory, when we're writing an equation for a weak base, the base will accept a proton from water. So we should be receiving a proton from water in this situation. And also, since it's a weak base, we're going to have an equilibrium situation, so we should have our double arrows. So water will be giving hydrazine the H and will be N2H5 plus because we've received a proton. And then the water, since it lost an H, will be OH and minus AQ. So we have hydroxide ions there. And we're going to make an ice table because at the end of this, we want to find what the pH is. And remember, the goal to find pH, you need the H3O plus. Now, in this equation, we don't have the H3O plus, but remember, there is a relationship that exists between H3O plus and between OH minus. So as long as we can find the concentration of OH minus, we can then find the concentration of H3O plus. So let's go ahead and make an ice table and just start filling out some information. So we have the initial concentration of the base was 0.500 molar. We don't care about water because it is liquid and its concentration won't change. We know at the beginning we'd have 0 this, but we'd have plus x and plus x because it's balanced already, and those are based on the molar coefficients of 1 and 1. And so here we'd have x and x. Here we have minus x. We're not sure how much of this will be converted into the N2H5 plus. It's not 100%. So we have to do 0.500 minus x. And so what we're going to do now is we're going to try to solve for x because we want to find this OH minus to help us find the pH in some way. It might not be direct, but at least it'll help us get there. So we need to make an expression. Now we're dealing with a base here, a weak base. So our expression will not be a Ka, it'll be a Kb. When you're dealing with a weak base at the start here, you're making a Kb, not a Ka. So Kb is going to be equal to OH minus times N2H5 plus over the N2H4. And we can replace those by the x values and the expressions at equilibrium. So x times x over 0.500 minus x, which is x squared over 0.500 minus x. We were given the Kb, so now we can plug everything in. So we have Kb is 1.7 times 10 to the power of 6, negative 6, sorry, is equal to x squared over 0.500 minus x. And now we have to solve for x, but remember, we don't want to do all that work with quadratic formulas, so let's always test our 100 rule first. So that's going to be the initial concentration over the Kb given in the question. And if you do that, you'll see that is greater than 100. Therefore, we can simplify. In other words, we can remove the x from the denominator. So we'll get 1.7 times 10 to the power of negative 6 is equal to x squared over 0.500. So that means that x squared is equal to 0.500 times 1.7 times 10 to the power of negative 6, which means that x is equal to the square root of that, which is 0.500 times 1.7 times 10 to the power of negative 6, which is equal to, so let's figure that out, 1.7 times 10 to the power of negative 6 times 0.5, square root of that, we get 0.000921954. Let's try it again. Let's redo this. Copied it down wrong. So 0.000, so 3 zeros, 9219. 921954 molar, because that's the concentration of the OH minus. Now you need to be careful here. You have the concentration of OH minus at this point, okay? And you want to find the pH. So there's a couple different ways you can do this. And maybe you can predict the way if you'd like. I'll do the two ways just to show you how you would do it. It really is up to you, but you just need to realize that you can't find pH directly, so you have to do a couple extra steps. The first method that you could do is you could find the POH, which is the negative log of the concentration of OH, which is the negative log of that concentration we calculated, so the 0.000921954, which gives you 3.035290537 as a POH. But remember, we want the pH. So let's call this step 4. Step 5 would be, well, we know pH plus POH is equal to 14. Therefore, pH is equal to 14 minus POH. So now that we have that, we can just plug that in. So pH is equal to 14 minus the 3.035 we found earlier. And that gives us 10.9647, so on and so forth, or approximately to, how many sig figs do we have? We have 2 sig figs is the smallest number of sig figs over here. So to 2 sig figs, about 11. So our pH is approximately 11. But we had to find the POH first, and then from the POH we can convert to the pH. So that's one way you could have done it, and you would have had full marks, no problem. Another way you could have done it is remembering a relationship that we mentioned earlier. So let's call this method 2. Remember that the concentration of H3O plus, or H plus, I'm just going to shorten it there, times the concentration of OH minus is 1.0 times 10 to the power of negative 14. Therefore, if you want to rearrange this, you can get the concentration of H plus is equal to your 1.0 times 10 to the power of negative 14 over the concentration of OH minus. And so in this situation here, that's 1.0 times 10 to the power of negative 14 over 0.000921954 molar, which would be, so 10 to the negative 14 divided by 0.000921954, and we get 1.08465213 times 10 to the power of negative 11. No need to write all those digits down, but I do, and I keep them in my calculator because I don't want to round. So just if you don't write all of them down, just make sure you keep all the digits in your calculator, especially when you have a lot of steps. But this is the concentration of H3O plus. That's what we just found. So we found the H3O plus, and now that we have the H3O plus, we can do our pH is equal to negative log of H3O plus, or H plus, which is the negative log of that number we found up there, 1.08 times 10 to the power of negative 11. And we should get, so second log, the same answer, 10.9647, so on and so forth, as our pH, or approximately to 2 sig figs, 11. So we have our pH is equal to 11. So both would work. Just depends on what you prefer. You can do both if you have time to check your answer to see if you're on the right track. But again, both are acceptable methods. So here we want to find the pH of a weak base. We had to use Kb values this time. When you want to find the pH of a weak base and you're using Kb values, there is the extra step that once you find OH, you need to make sure that you account for that and either find POH first and then convert to pH, or use your OH to find your H plus and then find your pH that way with the negative log formula. So everything is very similar with the exception that you're dealing with KBs, you're finding OH first, and you have that extra step at the end. So that was how to find the pH of a weak base using an ICE table and some KB values.